This is a second recording for section 1.2. This is where we left off. Fractions, decimals, and percents. Decimals, fractions, and percents are different ways to show the same value. Right? If you look at that pizza there, that's 1/2, which of course we know is 0.5 because 1 whole is the number 1. And as a percent, that's 50%. All right, and here we have 1/4 of a pizza, 1/4, which is 0.25, right, which is 1/4 of a dollar. And as a percent, that's 25%, which we're very familiar with. Recall to convert between decimals and percents. Remember to express a decimal as a percent. You move the decimal 2 places to the right, i.e. you multiply by 100 and add the percent sign. To convert from a percent to a decimal, you are dividing by 100 and you remove the percent sign, which makes sense because we know that percentage always means parts out of 100, right? If you think about 25%, you know that's 25 parts out of 100, which is then 1/4, right? So percentage means parts out of 100, so you know you divide by 100. Whereas if you have the decimal, like part A here, convert 0.08 to a percent. Here you know that you multiply by 100, right? So multiply by 100, you can do it in the calculator, or you know that that's just to move it over 2 decimal places, which is 8%, and you need to make sure you write your percent sign in there. But to convert from a percent to a decimal, remember that that actually means that instead of multiplying by 100, you divide by 100. And when you divide by 100, it makes you move the decimal 2 places to the left. So, and then you have to insert a 0. All right, so it's 0.0153 is the decimal, and make sure that you drop the percent sign. Right? And the one thing that you can remember is that the 1 whole represents 100%. So if you know that you have something less than 1 whole, you have less than 100%. Right? If you have 0.4, right, you know that that's less than 100%. If you multiply it by 100 or move the decimal over 2 places, you get 40%. Finding the percent of a value, recall to find the percent of a value. You always change the percent to a decimal form, right? We always remember doing that growing up. And multiply by the value. Remember that of in math always means to multiply. So if you want 23% of 18, you know that you're going to multiply 23% times 18 because of is multiplication. But you need to always be sure to change this to a decimal. 23% means 23 parts out of 100. If you divide by 100, if there's no decimal, of course, it's assumed to be at the end of the number. If you divide by 100, you move it over 2 places. So that's, of course, 0.23. So 23% of 18, we just do 0.23 times 18, and you get 4.14. And you should see if that makes sense, because 23% is like 1/4 of 18, right? And so if you think about dividing 18 by 4, 4 sounds like a reasonable answer, 4 and some change, right? Just 206% of 712. So I know that 200% of 712 would be if I doubled 712, so you'd get 1424. So I know my answer is going to be more than 1424. But of, again, means times 712. We just need to change this 206% to a decimal. So we do 206 divided by 100. If there is no decimal in the number, it's assumed to be at the end. So if we divide by 100, it moves it over 2 places. So that's 2.06, which makes sense because we know that 100% is 1. So 206% better be 2 and something. So if you do 2.06 times 712, you get 1466.72. So we're going to look at some different types of graphs. The circle graph, which we often call a pie chart, indicates the following circle graph indicates how Americans disagree as to when old age begins. So we have all these percentages, right? Decline in mental functioning, decline in physical ability. That's when these people polled decided when they felt that old age began. So according to the U.S. Census Bureau, in 2012, there were, looks like 229,937,770 Americans 20 years and older. So estimate the number of Americans 20 years or older in 2012 who define old age by decline in physical ability, which is this section of the pie. And it says by rounding. So we can actually do it both ways, without rounding and with rounding. But we really want to know 41% of this amount of people, 229,937,770. But that's what we're trying to find. All right, so we can actually do it. Let's just actually find the exact value. Let's cross off by rounding. So of implies to multiply. 229,937,770. I mean, you could round it to 230 million and round that to 40% maybe, but we can find the exact value. 41% of course means 41 divided by 100, which means move it over 2 places, so it's 0.41. So if we multiply 0.41 times 229,937,770, that should give you 9427445.7, so we can just round that to 86. There we go. So it looks like 94 million something people is the exact value. If you did want to estimate, I guess we could do that by rounding. I would probably do 40% or 0.40 times 239. Oh, it was 229. So that's something that you could do as well. If you do 0.4 times 230. That would give you 92. So that would be the estimate by rounding. But right, whenever you want a percent of something, you just change the percent to a decimal and you multiply. So here's something with bar graphs, life expectancy in the United States by year of birth. What was the difference in life expectancy between males and females in 1980? All right, so we just want the difference between 77.5, which is females, and 70 for males, so it's 7.5 years. What's the difference between males and females? Years less for males. Part B, estimate a man's increased life expectancy rounded to the nearest hundredth of a year for each subsequent year. So we want to find the life expectancy, the increased life expectancy. So it's sort of how many years per year. So man's, which is the red, we want to know the difference. So per year, right? So we want per year. And if you even look at the bar chart, it's every 10 years. So you wouldn't just subtract like 1960 to 1950. You would then have to divide that by 10. But what we do is we look at the first year and the last year, and we find the difference, and then we find the difference in the number of years. So this is from 2010 to 1950. So that would be 70. So 10, 20, 30, 40, 50, 60 years. Is the difference. So we want to, it went from 65.6 to 76.2. So we want to find that difference. And we want, that's the difference over 60 years. So if we want per year, we would have to divide this by 60. 76. And just watch, make sure that when you're punching it in the calculator, you subtract 76.2 minus 65.5, you get an answer. And then you divide that by 60. Don't hit the subtraction and hit divided by 60 without hitting enter in between, because your calculator will follow the order of operations. You have to do that subtraction first. And well, it says to round to the nearest hundredth of a year. Well, I've got 0.16766 ... So if we want to round to the nearest hundredth, that's this place. The digit after is larger than 5, so it becomes 0.18 per year. Oops. So we expect the life expectancy for males to increase 0.18 years every year. Estimate the life expectancy of a man born in 2020. If you kind of look at this, because these are going up every 10 years. If you look at this, it looks like it's pretty much linear, like increasing by the same amount per year. And that's why we did this, right? Is it looks like a straight line. I should have mentioned that before that for part B. So if we wanted to estimate in the year 2020, right, we would take our amount in 1950, which is 65.6, and we can figure out that that's actually 70 years. 2020 is 70 years from 1950. And if it increases 0.18 per year for 70 years, this is how we would compute the life expectancy in 2020. Right? We want to add 70 of the 0.18s because that's how much it increases per year. All right, 70 of those to the original amount since there's 70 years from that. So 65, and make sure you do the multiplication, of course, before the addition. So 0.18 times 70 is 12.6. So you want to do 65.6 plus 12.6, and that will give you approximately 78.2 years. So in 2020, we can expect the life expectancy for males to be approximately 78.2. So we did pie graphs, bar graphs, and the last one is line graphs. Line graphs are often used to illustrate trends over time. Time is placed on the horizontal axis, i.e. the x-axis. And this example is the line graph shows the percentage of U.S. college students who smoked cigarettes from 1982 to 2010, right? And we expect this to keep decreasing. Find an estimate for the percentage of college students who smoked in 2010. So 2010 is here. So we look over at the percentage, and it looks like it's exactly halfway between 16 and 18, but we are estimating, or 16 and 20, which is 18%. In which 4-year period did the percentage of college students who smoke decrease at the greatest rate, right? We're wanting the one that has the steepest slope, and that looks like this place right here is where we have the steepest slope. And so that's between the years 2002 and 2006. In which year did 30% of college students smoke? So we go up to 30%, which is halfway between 28 and 32. And we go over, and this time we want to look at the year. So we go down and decide that that's 1998. So developing mathematical models that estimate relationships between variables. A linear equation, linear means line, is an equation between two variables that gives a straight line which plotted on the graph, right? So if we hear the word nonlinear, it means not in a straight line. Real-life applications in which the amount decreases or increases by a fixed amount can be often described with these linear models, right? If 1 can of beans costs 50 cents, 2 cans of beans cost $1, 3 cans of beans cost $1.50, right? That's exactly a linear model, although that doesn't look like a straight line. That is exactly a linear model because each can of beans costs 50 cents. But so there's some things that are approximately linear. We use linear models, although they may not be exactly linear. Like you can see in this picture here, that a line is best fit. I mean, these points fall in a linear fashion, although it's not exactly linear. It's pretty close, so we use a linear model, and we are going to talk about that a little more when we get to the statistics section in this course. So let's write a linear equation. Remember, linear means that the variables to the first power, you might remember y equals mx plus b is a line from algebra, right? X and y are to the first power, so you might have something like y equals 2x plus 7, y equals 3x plus 5, that kind of thing. That's a linear equation. Billy prepares 2 kilograms of dough every hour he works at the bakery. Write an equation that shows the relationship between the number of hours worked X and the dough prepared Y. So the dough prepared depends on the number of hours worked, right? So we know that if he did 2 kilograms every hour and worked X hours, we would do 2 times X, which we would just write as 2X, right? If we worked 4 hours, we would say 8 kilograms, because that would be 2 times 4. 10 hours, 2 times 10, right? That's how we would get the answer. So we know that our linear equation is y equals 2X. And you should check it with a couple of things, right? And you could even use H for hours. If the hours is 5, y equals 2 times 5 equals 10 kilograms. Yes. All right. Jamar earns $50 a day plus $2 for each item he sells. Find the amount he earns per day for selling X items. So you can use Y again, or you can use E for earns. He automatically gets a flat $50 a day, right? And think about how you would do this. If he sold 10 items, and he gets $2 for each item, you would do 2 times 10 to get $20, and you would add that to the 50. Right? If he sold 5 items, you would do $2 times 5 to get the $10 and add that to the 50. So you're going to be adding it to the 50, and it doesn't matter which way you write it, 50 plus something or something plus 50. But the 50 is an automatically flat fee he earns per day, and then he earns $2 times however many he sells, all right? And you should always just check it, because you can look at this problem and see, okay, if he sells 10 items, $20, 20 plus 50 is 70. Right? Do the same thing, and then you can plug it into here and see that you will also, if you plug in 10 items, you will also get 70. All right? So that is a linear model. It's because E and X are to the first power, and it increases by the same amount. It's $2 per item. He doesn't earn $2 for the first item, $1 for the second item, 50 cents for the third item. That's not what's happening. He's get $2, a fixed $2 for each item. That's what makes it linear. Use your equation in part B to show the amount earned for selling 14 items. So the amount earned is $50 plus 2 for every 14 items. And of course you have to multiply first. So that's 28. So $78. All right, X is the number of items, so you just do 2 times 14. All right, our last example in this section, modeling the cost of attendance of attending a public college, which has increased greatly over the years. Estimate the yearly increase in tuition and fees. If you look, I mean, it's not exactly linear, but it looks pretty close. Right, the amount increasing, because these are going up by 1 year and these are going up by $400. So you have to watch the scaling as well. But this is, and down here it says that although the growth is not exactly linear, it is close. So we will choose a yearly model. So again, if we want the yearly increase, it went from 33.62 to 70.20, but that happened over a 10-year span. So that's exactly what we'll do like we did last time. We find the difference. So it increased $3,658, but that's not dollars per year. We need to take that. That's over a 10-year span, so we're going to divide that by 10, of course, which we can do in our head. Dividing by 10 just means move the decimal over one place. So 365.8, and that is dollars per year, right? This is dollar for 10 years, and that's dollars per year. Because it says yearly increase, all right? It's not, and then we have to take its average over this time interval, all right? So we subtract that and divide by 10, just like we did before. Write a mathematical model that estimates the average cost of tuition and fees for the school year ending X years after 2000. So the average cost, so you can choose whatever letter you want. But if you think about how you would find the cost, you would take the original amount and you would add to that. It's increasing at $365.80 a year. So you would, and X is the years after 2000, you would do 365.8 times the number of years after 2000, which is the first year, which makes perfect sense, right? If I asked you about in the year 2015, you would take this original amount and you would take 15 of these yearly increases, right? 15 of the yearly increases and add it to the original amount. So it just says write a mathematical model. It doesn't give us a specific year, so that is our linear model. It's X and C to the first power. Again, you can use Y, you can use C. Oh, and it actually tells us to use T. I didn't even see that. Average cost of tuition and fees, T. So instead of C, we should be using T. But that is the linear model. It's very similar to that last example. Use a mathematical model, which we just got to be 3362 plus 365.8 times the number of years after 2000. To project the average cost of tuition and fees for the school year ending 2016. Well, the original year was 2000, so it's 16 of those yearly increases. Again, do the multiplication before the addition. 365.8 times 16. Do that multiplication, you should get 5852.8 and add that to the 3362. So that should be $9,214.80 for the average tuition in 2016. Yikes. Okay, that is the end of section 1.2.